Hello, my name is Muhammad Ismail. My matrix number is 07 DTP19F1034. So I will present about 3.0 mold. What is plastic injection molding process? Plastic injection molding is the process of melting plastic pellet, thermosetting or thermoplastic polymer that once malleable enough are injected at pressure into a mold cavity, which fill and soluble process in final products. So, compare injection mold in plastic process is a plastic process including the injection molding, transfer molding, and instruction and molding, blowing molding, and then the defect of plastic injection molding. So, for the first is injection molding process. Injection molding process is used to produce thin molded plastic part for a wide variety of application. One of the most common being plastic housing. And then plastic housing is thin welded enclosure, often requiring many ribs and bosses on the interior. These housing are used in a variety of products including household appliances, consumer electronic, power tools, and as automotive dashboard. Other components welded products include different types of open containers, such as buckets. Injection molding is also used to produce several everyday items such as toothbrush or small plastic toys, many medical devices including valve and syringe manufactured using injection molding as well. So for the transfer molding process is transfer molding is similar to compression molding in that carefully calculate pre-measured amount of incurred molding compound is used for the molding process. The difference is instead of loading the polymer into an open mold, the plastic material is preheated and loaded into a holding camper called the pot. The material is then forced or transferred into the preheated mold cavity by a hydraulic plunger through a channel called screw. The mold remains closed until the material inside the screw. Transfer mold part inherently have less flash, excess material that run along the parting line of the mold than the compression mold counterpart, because the mold remains closed when the plastic enter the mold cavity. However, transfer molding still produces more waste material than compression molding because of the screw, the air hole, and the overflow groove that are often need to allow air to escape and material to overflow. After that, diagram for the transfer is this. The preheated incurred molding compound is placed in the transfer pot. After that, a hydraulically power plunger push the molding compound through the screw into the preheated mold cavity. The mold remains closed until the material inside is cool. The thermoset or thermoplastic. After that, the mold is split to free the product with the help of the injector pin. The flash and spool material is trimmed off. After this is extrusion and blowing molding. The first step in the extrusion blow molding manufacturing process is the extrusion of the tube, also called perisson of viscous plastic into a product mold. The mold closes around the perisson and air is pumped into the inflate the perisson against the mold walls. Once the plastic cools back to the solid state, the mold opens and the part is injected. Finally, the excess material along the mold pinch line is removed by a process called the flashing, and the part is ready to undergo any secondary operation that needed to finish the part. Then B, the defect of plastic in injection molding, flow line and sink mark. For the flow line are straight pattern or line combination often in color that show up on the prototype part as a consequence of the physical path and cooling profile of the molten plastic as it flow into the injection mold tooling cavity. Injection mold plastic begin in journey through the path tooling via an intrinsic section called a gate, and then it flow through the tool cavity and cool, eventually hardening into a solid. After that, for the sink mark, a small crater of the diffraction that develop in thicker areas of the injection molded prototype when sink catch occur into the inner portion of the finished product. The effect of is somewhat similar to sinkhole in the photography, but caused by shrinkage rather than erosion. After that, vacuum void. Vacuum void are pockets of the at tap within or close to the surface of an injection mold prototype. After that, the first surface delamination. Surface delamination is a condition where thin surface layer appear on the part due to the contaminant material. So this layer appear like a coating and can usually be peeled off. After the wet line. Wet line are actually more like a plane than a line that appear in a part where molten plastic meet each other as they fall from two different parts of the mold. And then short shot. As the term implies, short shot can be described as a situation where a molding fall short. This means that the molten plastic for some reason does not fully occupy the mold cavity or cavities. So the resulting in a portion where there is no plastic, the finished product becomes deficient because it's incomplete. After the warping or warpage is the deformation that occurs when there is uneven shrinkage in the different part of the mold component. The result is a twist, uneven or bent shape where one was not intended. After that, burn mark. Burn mark caused either by the degradation of the plastic material to the exercise eating or by injection spit that to So after this, I will talk about the primary factor of molding design. So for the resource space is they have a short void, complete necessary, molding circle, number of impression to be included in the tools, position and type of fit, and molding opening force. For the first is short void. Short capacity is the maximum volume weight of the material that the screw can inject into a operation circle. The short capacity is also known as injection capacity. The short weight of a product is the amount of the material required to be injection into the mold to manufacture the product, including the fit system. Also, while calculating the short void, the actual product spare runner and gates and everything are considered. Short void is also lesser than the short capacity. Is it dependence on factors like material density, machine screw diameter. Maximum dosing also play as a part in determining the maximum short weight of the machine. The backward refilling position in the barrel to fill the given short weight is called injection stroke or short size. To calculate the short size in injection molding, we should know the density of the raw material if we are using a high heat and a high flow raw material which is density of 1.52 gram per cube centimeters. Then we need the diameters of the screw. Let's take it as 28 mm or 2.8 cm. Let's assume we have a short weight of 40.6 gms. Thus, we can calculate volume as mass or density, which will be 40.6 or 1.52 equal to 26.01 cube centimeters. To calculate the injection stroke or short size, we can put all value in the formula of short volume. For example, short volume pi equal darab R2 darab short size. So for the clamping necessary, clamping force refers to the force applied to a mold by the clamping unit of injection molding machine in order to keep the mold closed. This force must oppose to the separating force caused by the injection of molten plastic into the mold. Normally, the force rating is set in ton, e.g., 200 ton machine is capable of producing a maximum clamping force equivalent to a total of 200 tons. The calculated tonnage can be used to select a capable machine will be prevent part defect such as excessive flash. So how much flame force is required? The required clamping force can be calculated from the cavity pressure inside the mold and the short project area on which this pressure is acting. There are variables that affect the clamping force calculation, like the material types, low flow versus high flow plastics, and the depth of the part. Molding circle. Molding circle is injection molding involve a high pressure injection of a polymer into a mold where it is shaped. The individual parts of this process are very short. The whole injection molding process usually lasts from 2 seconds to 2 minutes. There are 4 stages in the circle. This stage are the clamping, injection, cooling, and injection stage. Clamping. Before the mold is injected with the material, both half of the mold have to be closed. They are closed by the clamping unit. Both half are then attached to the injection molding machine, and one half can slide material in this and is then injected as the clamping unit push the off together, and both half held tightly while material is injected. Larger machine take longer to close and clamp the mold. Injection. For injection, plastic pellets are fed by means of a hopper into the injection molding machine. This pellet move toward the mold by the injection unit. The heat surrounding the barrel and the pressure serve to melt the pellets. The volume of material injected is called the shot. This injection time finished when 95% to 99% of the mold is filled. Is it hard to calculate exactly the injection time because the flow of the plastic is always changing the dynamic? Injection time can be estimated by other factors such as injection pressure, power, and shot volume. The injection pressure can range from 35 to 140 MPa. The rate of injection and the pressure which can be reached are determined and controlled by the hydraulic system in the machine. So for the cooling process involves the plastic inside the mold beginning to cool after it make contact with the interior mold. As the plastic cool, when it hardens, it will take the desired shape. The part may shrink slightly during cooling. Only when the cooling period has elapsed can the mold be opened. It is from the wall thickness of the part and the thermodynamic properties of the plastic that the cooling time can be estimated. Injection. The last stage is injection from the machine. This is done with an injection system. When the mold open, the part is pushed out. Force must be used because the part shrink and stick to the mold. The mold can be shut against after injection, and another shot can be injected for the process to begin again. Mold design is a key factor in determining the quality of the finished product. The strength, durability, shape, and size all rely on the type of mold that is used. The mold must be sturdy and be able to withstand the pressure involved during the injection process. The polymer must also be able to flow properly along the mold. The mold must also be carefully designed to allow heat transfer to control the cooling process. This is a complex process and it takes highly trained individual to oversee the entire process. At APL, while it is important to keep output level high, safety is also a primary concern. At Automatic Plastic, we do our very best to offer quality plastic part across a wide range of industry using process. So number of impression to be included tool. First is the decision concerning how many impression a mold tool should have is frequently given insufficient tools. The usual approach is as follows. The production rate of any mold tool is given by the expression. When a new mold tool is being considered, however, the expression is rearranged to estimate the number of impression necessary to achieve a desired production rate. If we take the example of a required production rate of 1,800 per hour being necessary to meet production schedules, the number of impressions required to achieve this with an estimate cycle of 15 seconds is. Clearly, this result will be round up to 8 impressions or sometimes a higher number to accommodate rejection and provide buffer stock. Having established this, the next stage is to establish which machine the mold tools will run on. Apart from the physical size of the tools, the other main limiting factor are the short weight and the project area of the mold. Once this factor have been resolved, the mold tools may be designed to fit on the selection machine. In many cases, this approach is satisfactory, but a significant number of projects do not prove satisfactory in production when designed on this basis. This is often because the mold part do not meet the quality requirement. There are three main reasons. For the first is the mold tool design is unsatisfactory. The second is the machine is not capable of producing the part to the required quality, and then the last is the machine is adequate but the number of impressions being used. And then is position and type of feed. First is feeding system of the injection mold. The function of the mold feed system is to make the high temperature melt under high pressure go into the mold cavity to fulfill that. The style and quantity of get and feed style often determine the specification of plastic mold base. Whether the design of the get system is reasonable will directly affect the appearance, quality, dimension, precision, and molding cycle of the molded plastic part. And then concept and classification of feed system. The feed system of the mold is a section of the mold following passage from the nozzle of the injection molding machine to the cavity. It can be divided into two main types, cold runner system and hot runner system. Ordinarily, the cold runner system is also divided into the side gate system and point gate system. The gate system is composed of the main runner, sub-branch runner, the cold material well, and the gate. The hot runner system has no main runner and sub-branch runner. The melt passes through the manifold plate and the hot nozzle directly from the gate into the cavity. And then the design principle of the feed. The design of the feed should follow the principle. Number one, ensure the appearance quality of the product. Handicap will leave thrust on the surface of the product. Thus, it will affect the surface quality. In order to not affect the appearance of the product, design should try to set the gate in invisible part of the product. If it is impossible, the gate should be easier removed, and after the removal, the left thrust should be the minimum. After that, number two is ensure the quality of the product. The style and quantity of the gate should be reasonable, which need ensure that the plastic melt quickly, fill the cavity, and pressure and heat loss are reduced. The internal organization of product is fine. The design of the gate system should prevent the defect of the product like the shrinkage mark, short filling, flash flow, poor wet line, and residual stretch, deformation, and even shrinkage, jetting, drooling, resin, degradation, and other defect. The gate system should be able to smoothly guide the molting plastic to fill cavity in every corner, so that the gas can be discharged, avoiding the bubble by trapping air. The feed system should collect the melt material of the low temperature, prevent its entering the cavity and affect the quality of the product. The gate and runner system are arranged balanced possible. Melt plastic can be evenly filled in each cavity, so that the shrinkage rate of each cavity is uniform. The good feed system design could improve the size accuracy of the plastic part and ensure the injection part to be interchangeable. Number three, the minimum flow resistance. Flow part of melt plastic should be as short as possible. Turning should be reduced and the cross-sectional area of the runner should be reasonable. The appropriate cross-sectional area should be small. The reason is increasing the small to the big is simple, but the contrary is hard. The small runner reduces the proportion of waste material. The circular mat can fill the cavity in the shortest time to shorten the molding cycle and improve the productivity of the mold. The less air in the feed system would reduce the venting burden of the plastic mold. If the temperature and pressure loss of the melt in the flow channel are small, the molding quality of the product is easy to guarantee. Number 4, not affect the automatic production. If the mold designed for the automatic production, the feed system, runner and gate should be able to fall off automatically. This is the injection molding formulas. Then I will explain about sketch type of injection mold. 2-plate mold and 3-plate mold. For the first is 2-plate mold. The 2-plate mold are the most commonly used type of injection mold. They consist of one parting plane where the mold split. In a multi-cavity 2-part mold, runner and gate must be in the parting plane to ensure runner and gate injection will not split. For the 3-part mold, the 3-part injection mold consists of 2 parting planes and the mold split into 3 sections. Therefore, runner and component can be located on different parting planes. In the 3-plate mold, the runner is ejected separately to the molded part. Therefore, automatic degating is possible. Its application include the positioning of the runner system in different planes to injection location and automatic degating. This is the 2-plate mode and the 3-plate mode. Application. And that's all for me. Thank you.
Hi, my name is Muhammad Aiman bin Abdurrahman and I will talk about 3.4, which is complete mold design. So in here we talk about the core, cavity, feed system and ejector pin. As you can see, for the part, we are using the Redmi 5 Plus by Xiaomi with a correct dimension following for the phone that I'm using to this project. So for the part with the feed system, and then this is the part which is the Redmi 5 Plus, and then I will talk about the feed system. So the main thing in feed system is a sprue, gate system and a runner. A melted plastic enters the part through a network of channels in the tool called the runner system. There are usually 3 parts to this. The sprue, which is the primary channel where material flows into the tool. Secondly is the runners, smaller channels which guide the plastic to the gates, and then the gates that the entry point to the part. Next is the ejector pin. Throughout the injection process, the tool are clamped tightly together. Once the plastic has cooled sufficiently to maintain its shape, the tool opens, usually by the core and part moving backwards away from the cavity. Ejector pins are then pushed through the core against the part, releasing it to drop free from the tool. This process does result in a few witness marks on the part. The one is parting lines, where the 2 halves of the mold meet, and then the ejector marks, where the pins meet the part. Normally these are hidden on the rear. For the mold shrinkage is the phenomenon where the volume of the molten plastic filled inside the cavity of a mold is shrinking at the time as being cooled and solidifying. The value of the molding shrinkage factor is generally a number in the range of 2/1000 to 20/1000, which is about 0.2 to 2%. A mold shrinkage calculation which is the difference between the dimension of the molded product and those of the cavity of the mold is expressed by the molding shrinkage ratio, which is 100 times 400 minus 399, and then divided by 400, and the answer which is 0.25%. And then we're talking about the cooling system. These are two standard methods for cooling system. For the first one is air-cooled mold. Molds are not frequently used as they take a long time to reduce the heat in the injection mold via heat transfer dissipation to the surrounding air. If the surround environment for the injection molding machine and mold itself is kept cold, that can increase the amount of the heat shed to the air. That may also require additional operating expense to cool that space. And then secondly is fluid cooled. Fluid cooled molds are the primary source of cooling, with ethylene glycol and water as the most common used fluid mixture. The water provides the cooling as it flows through the mold, taking heat out of the mold. The ethylene glycol prevents rust from forming inside the mold, cooling piping, and helps to keep the mold at a steady temperatures during manufacturing use. And then lastly is split mold is a great way to cast complex shape of small to medium size quickly and effectively. This method is virtually identical to the one-part open mold making technique, being that it is essentially a one-part mold with strategic splits cut through it. These splits allow for greater complexity of shape to be used because the rubber, which is usually silicone, mold can be stretched open along the splits to extract the master and the subsequent castings from the mold. This method is commonly used when casting figurines and action figure prototypes. This technique sometimes requires the use of air vents to assist in evacuating the air pockets that are caused and trapped by certain shapes, although initially more difficult and longer to prepare. Molds with air vents are likely to produce higher quality casting than plain split molds. So for the 3.5, which is perform 3D design of two-plate injection mold. So this is the subtopic, which is the design a plastic part, a two-plate mold of the plastic part, a detailed drawing of the mold, the assembly of the mold, and explode drawing of the mold. So for the A is design a plastic part. A plastic design is the building block of plastic manufacturing and can make or break not only the initial investment required to get a product launched, but the long-term profitability of that product. B is a two-plate mold of the plastic part. Consists of one parting plane where the mold splits. In a multi-cavity, two-plate mold, runner and gate must be in parting plane to ensure runner and gate ejection when mold split. So C is the detailed drawing of the mold, which we use Autodesk Fusion 360 for making this design. As you can see, there is the ejector pin, the part, the runner, the feed system, gate system, and parting line, and then there is the core and cavity. So for the D is the assembly of the mold. Mold assembly is one of the most critical steps of molding making procedure. All the parts, machine or purchase need to be put together and required to be work for functionality. And the lastly is an explode drawing of the mold. An exploded view drawing is a diagram, picture, schematic, or technical drawing of an object that shows the relationship and or order of assembly of various parts. It shows the components of an object slightly separated by distance or suspended in surrounding space in the case of a three-dimensional exploded diagram or a visual representation of an object exploded by explosives. An object is represented as if there had been a small controlled explosion emanating from the middle of the object, causing the object's parts to be separated an equal distance away from their original locations. And finally, we talk about the last subtopic, which is the 3.6, is the sustainable elements for mould project. So, the elements of sustainability assessment and management embedded in the general sustainability framework recommended by the Committee on Incorporating Sustainability in the US EPA is an approach to incorporating sustainability to inform decision making. It is called sustainability assessment and management. And this chapter describes the steps involved in this approach, beginning with a screening evaluation to determine whether to conduct the sustainability assessment and management process and to determine the appropriate level of effort or depth of such an assessment. This step is followed by problem definition and scoping, which includes identification of options. Preliminary scoping of the analysis, stakeholder involvement, and opportunities for collaboration. The next section describes a set of analytic tools that can be used in the sustainability assessment and management process. The set of potential tools include risk assessment, life cycle assessment, benefit cost analysis, ecosystem service valuation, integrated assessment models, sustainable impacts assessment, environmental justice, and present and future scenario tools. This list is not meant to be comprehensive, nor will all of the tools be useful in all cases. The tools, however, are the types of tools that should be in EPA's sustainability toolbox and are likely to be useful in some instance. Following the discussion of tools, the next topic is how to integrate the sustainability assessment and management process into management and policy decisions. Integration into decision making involves summarizing the major results of the assessment in terms of a trade-off and energy and synergy analysis that highlight impacts on important social, environmental, and economic objectives. Once decisions are taken and implemented, there should be follow-up evaluation of outcomes on important dimensions of sustainability. The sustainability assessment and management process should incorporate certain key features. The number one is comprehensive and system-based analysis of alternative options should include an integrated evaluation of the social, environmental, and economic consequences. Number two is intergenerational. The long-term consequences of alternatives should be evaluated in addition to the more immediate consequences. And number three is stakeholder involvement and collaboration. Stakeholders should be involved throughout the process. And lastly, we talk about the awareness of environment. Numerous technologies are used to produce molds and to produce the materials they are made of. Lastly, we talk about the awareness of environment. Numerous technologies are used to produce molds and to produce the materials they are made of. So it is important to understand the factors that influence the environmental impact related with the production of injection molds. The manufacturing technologies, the material of the machining tools and cutting fluids, and the process parameters setting will define the level of environmental impact. Furthermore, the mold's material and the mold's performance during the injection phase, cycle time, plastic material waste, energy required, and etc. have also an effect in the overall environmental impact. So, a life cycle approach is recommended to understand the mold on an environmental perspective. In this paper, a life cycle assessment model is presented to predict the environmental impact of a plastic injection mold during its entire life. The model is described through the explanation of the required inputs, variables, correlation, and use algorithms.